apply our knowledge of rate laws in order of reaction to determine the order of reaction based off data and based off the graph. So based off the concentration, so if you look at the concentration and then at the rate, you can see how the concentration affects the rate. So if you look at this concentration, as you increase concentration of A, the rate does not change. So if the rate does not change based off this concentration, it's zero order. Now look at this graph, concentration 1, 1. If you increase concentration, the rate increases at the same ratio as concentration, 1 to 1, 2, 2, 3, 3. So therefore it's first order. Now if you look at this graph, as you increase the concentration, the rate increases more than just a 1 to 1 ratio. As you can see, like this is almost as if you square the concentration, that's what you get as your rate. So if that happens, if you see that in the data, this is second order.
So hopefully we can get it all done tomorrow.
So based off how concentration affects the rate, that's how you can determine the order based off data table. We're going to go over a catalyst and basically what it does in a reaction. So basically what a catalyst does is it stabilizes a transition state and lowers the activation energy, which is energy required to start the reaction. So it lowers that energy and by doing so it speeds up the reaction. Some catalysts slow down the reaction, but most of them actually speed it up. So if you look at the graph, low reaction, and let's make this exothermic. So this is a normal reaction. What a catalyst does is it lowers this activation energy, and like it can do that. Or if it has an intermediate, it can make like a. Has an intermediate, it can have two smaller steps. But either way, what the catalyst does, like these two activation energies, like you combine them, is always going to be less than the original. So that's what a catalyst does, it lowers activation energy, right? So that's basically how the catalyst works. Like you're still releasing the same amount of energy. Like in the end, like this difference is always going to be the same. It's just the activation energy that's changing. That's a common misconception. The amount of energy released is still going to be the same. It's just the energy required to start the reaction is different.
No, I mean like the dance difference.
We're going to go over how to write rate laws. And so, see, in this just theoretical reaction, we have just certain data for each substance and according to concentration and how fast it's going to react, which is the rate. And so for determining the order of each reactant, you're going to want to look at the rate of change between the concentration and initial rate.
She's a happy, happy little girl. Sorry, guys.
So,
How'd the squeaker go for you?
so here, when the concentration is going up by 2, this goes up by 2 as well. And when the concentration goes up by 3, going from this goes to 3 as well. So since there's a direct correlation between how much they're changing, this one's just going to be first order. And for the B, we're gonna have the same concentrations here. And so 1, 2, 3, and you look, and from when this is doubling, this is going up 4 times. So this is 2.
Ramaya Bentley, please go to room 123. Ramaya Bentley, please go to room 123.
And and this is going up by 4. And so we're looking at the next, from when this goes up by 3, this goes up by 9. So as you can see, this number is getting squared over here, so it's going to be a second order with respect to this reactant. So now when you're looking at the actual the rate law equation, it's going to be always going to be R equals K, and then you're going to want to plug in each reactant. So you're going to have the concentration of A times the concentration of B, but since B is it's second order, you're going to put a square, and if it was third order, you would put a 3, and so on.
Alright.
So in this problem, we have just a pretty simple reaction, and when you're determining order, you're gonna, when it's with respect to whatever, you're gonna look for when that is changing, when it's in respect to that. So for P4, you're gonna look when this is changing, which is the concentration of P4, and you're gonna when this is constant, and so you're gonna analyze the different rates of reaction, and if they're the same, like these are here, they're not the same, but they're very close to it. It's just going to be 0 order because there's no change when there's a change in concentration. And with respect to H2 here, you're going to find when these are constant and these are changing, and if you look at the rates, you can see that they're doubling, and since this doubled and this doubled, it's just going to be first order, so it's the same amount of change. And so when you're writing the rate law, you're going to have R equals K, because you're always going to need the constant, the concentration of whichever substance, and for this it's going to be H2. And since it's first order, there's no power, and since P4 is 0, there's no, you won't put the concentration of P4 since it's irrelevant to the reaction. And so determining the constant, you're going to take the rates and plug in, you're just going to plug into this, and you take your concentration of H2, so, and it doesn't matter which one, you can just do whichever, so I'll do these two right here. So you get 3.20 times 10 to the negative third equals K times 0.0075. So there, you're just simply going to divide it out. And the answer for this is going to be 0.0426.
I need to covalent bonding. On either side is where to go.
And the answer for this is going to be 0.0426.
I need to covalent bonding. On either side is where to go.
No, we can do that with
Okay, so pretty much, the I minus is a catalyst. You can see it at the beginning and the end of the reaction. And the OI minus is the intermediate, because it's not at the beginning or the end. And you can see the intermediate in the reaction video that we saw because of the color change from like a lighter yellow with the iodine. It turns to like a darker orange, and that's the intermediate, and then changing back to the lighter color, because then you just have water and iodine again. So pretty much what this catalyst does, if you were to look,
this is copper nitrate.
the graph of the reaction.
Black, right?
And so pretty much this is the reaction without a catalyst. This is like the activation energy, the energy required for the reaction to occur. So pretty much what it does is there's two smaller reactions with lower activation energies that make it easier to happen. So these activation energies are easier to reach than that one. So it happens much quicker.